Good afternoon. We resume our lecture series on Six Sigma right now. This is a follow through of lecture 35, which you must have witnessed before me. I ended up with this slide. That says DMACC is a step-by-step disciplined procedure that defines, measures, analyzes, improves and controls a process that is currently producing defective goods. That was where I left. Let's now get into this and let's try to find the incentives. Take a close look at this slide. What you see is an iceberg. In fact, if you look at the total amount of the what we call costs of poor quality, generally speaking, what gets measured in the company are the scrap, rework, warranty services and so on. These are the visible costs. These are the ones that get really recorded somewhere. Probably in a plant report, this might be being recorded. But these other guys, they just stay hidden. Like an iceberg, most of it is inside water. Only the tip is visible. And if you look at the inside, there are things like conversion efficiency of material that also can be poor if quality is poor. Inadequate utilization of resources, that's also something if quality is poor. Excessive use of materials, cost of redesign and reinspection, cost of resolving customer problems, lost customers, goodwill gone, high inventory, all these are also consequences of poor quality. Unfortunately, these are not visible. But when it comes to doing a Six Sigma project, you got to get deep into these things. You got to get inside that iceberg. You got to find out items there that can be eliminated. And these are the ones that will have a bottom line impact on your company's balance sheet. That's like something that you got to pin down. If you're able to do this successfully, you'll end up with a very good project, very good Six Sigma project. So the incentives are going to come from this. What are some of the other things that you require? There are certain things which are like the human element, certain parts of it which are required. For example, on the human side of it, strong leadership is required, good training is required, and it just goes without saying, if people are not trained in statistics, they'll not be able to do a Six Sigma project successfully. Customer focus, find out the CTQs, who are the owners of the CTQs, projects teams have to be put in place. There's got to be an overall cultural change. That also is something that's got to be there. On the process side, analysis of variation, this is to be done. A disciplined approach has to be taken to try to impact the process. Quantitative measures have to be there. You should be able to measure them on a scale. Statistical methods have to be used. And of course, process improvement is the mission. So in fact, all of these things, they must be there. If these things are all there together, you're bound to succeed with a Six Sigma project. So make sure when you're doing a Six Sigma project, bring up this slide and use that as a checklist to make sure you've really taken care of each of those items to be able to move forward. What was the impact on the cost of poor quality? You saw that iceberg. Motorola had an iceberg like that. They had a huge iceberg. In fact, their market share had gone down from being 90% to 10% because the Japanese products, the Japanese handheld mobile communicator devices, they were very different from our cell phones. They were not like cell phones. They were high-powered, transistorized wireless communication devices. And Motorola had the virtual monopoly there. Their market share was like 90%, but because of poor quality, because quality was something that was sidelined, they focused on production and supply. They ended up losing that major market share to foreign wireless walkie-talkie makers, and that came down to something like 10%. Then they mounted this Six Sigma approach, and look what they were able to do with their cost of poor quality. That came down for something like being 15% in 1986 to, in about 10 years' time, it came down to about almost 1/3 of that. That resulted from their very aggressive attack on this whole problem with the Six Sigma methodology, the DMACC methodology. And these kind of give you an indication of the quality level that's where they started. They started out here, that was like 100 defects per million. That was a pretty high level of defects. That's like something that's not to be tolerated. This is one of your wireless sets would be defective per 1,000. That's a pretty high level. They started the work with Pareto, brainstorming and so on and so forth, cause and effect diagrams and so on and so forth. Then of course they started to bring in other techniques, and they had teams put in place, they had SPC installed on the floor and so on. That happened in the 90s, and in the 90s, late 90s, they brought in design of experiments and design for manufacturing, process control, these things they brought in. And they also brought in at that point, around 1995, they brought in the idea of the black belt program. This was internal to Motorola at that point there. Then of course, they also externalized this thing. They started consulting with other people there because they showed success there. And of course, the march continued, and when they brought in the master black belts, the sigma level, 6 sigma is out here, that's parts per million, but they were able to reach in the 90s, but before the 20th century was over, they were already at 5.65 sigma level. That's a pretty high quality level. So you got probably, 7, 8, 3, 4, 5, 7, 8 defects per million. This was Motorola's march toward quality. So it started with something that was fairly nominal quality to a level of quality that was certainly much, much better than what they started with. Who are the experts you require to be able to succeed with Six Sigma? You certainly require a Six Sigma champion. This is the person who really undergoes a lot of training. He understands statistics now. After he goes through the training, he understands that. And he's also taught how to manage projects, because remember, you also need project management skills when you're doing this. And this champion is going to be acting as advisors. He's going to be advisor, and he's also going to be managing he's going to be basically mobilizing resources to be able to support the project. Then you've got master black belts. These are the people who conduct this Six Sigma training. They also do a lot of job training experience. They actually have this. Then you've got master black belts. These are the ones who really get trained on all the statistical methods, and they become basically the major stakeholders in Six Sigma projects. They are the major powerhouses for expertise. Then you've got green belts who also become involved. So in fact, it turns out you got the champions, Six Sigma champions. You got master black belts, then you got black belts and green belts. Without having these people together, you can't really do a Six Sigma project. In fact, if you think that just by learning a little bit of, graph plotting and so on, and calculating averages and sigma, you'd be able to do a Six Sigma project, just absolutely please push that out of your mind. You should be able to do design of experiments. You should be able to do regression modeling. You should be able to do data analysis. Unless you're able to do these things, Six Sigma is certainly beyond your reach. That's something you should not try. Let me now get into a live case. This is a case that the problem occurred with the Nissan company. When you look at a Nissan vehicle, on the back of it, like many other cars, you'll see a logo. Now that logo actually is not welded to the car. It's actually stuck with a glue. There's certain things done with that logo there. So the logo might be like this, and the logo is put on the thing. Some glue is applied, and the logo is put there, and that's how it really stays there. What we have to really do is we have to really see if indeed there is anything wrong with this. Where would you begin? You begin with customers. The complaint was that Nissan's logos, they kept falling off. And these, of course, if they would be lost on the road, they'd have to be replaced with a new logo. What was the extent? So the first thing that was done for this project was, it was a defect reduction project. The first thing that was done was define the problem. The problem was Nissan's logos kept falling off. Then some measurements were done. How many of these things? Was this a very rare event? It was found that 1 in 50 vehicles would lose their logo. That was the extent to which they could identify the problem. What exactly is they define? I mentioned that define step there. Define chronic and big issues in your process. Create a diagram showing all the steps where the problems are. This is something you got to be able to do. So when you're doing define, this is the first step in DMACC. You must define the process itself and locate exactly where the problem is taking place. Select a project. Then you, of course, select the project to combat one or more of those process problems there. Define the parameters and the scope of the project. And this again is definition. And you've got to make sure, of course, you put your finger on the right CTQ. And your black belt should examine that to make sure that it actually is the right kind of CTQ that can be now attacked with a project there. Examining the CTQ. CTQs are those quality characteristics that really have an impact on customer satisfaction. So that is like your Y. Y is a CTQ. Y is a CTQ and X are those process factors that might be influencing that. I have to locate the correct X so that I can drive this Y to the target value or to a level of defect that is acceptable to the customer. So I've got to establish this what we call cause and effect relationships between the control variables and the CTQ as it is measured. How do we do this? We use the Pareto to try to identify the most critical CTQ, the thing that customers are generally unhappy with. I frame a project to be able to do this. For that, I'll have to really, define the charter of the project. I have to define the scope of the project. I've got to define the work breakdown structure. I have to come up with a CPM little network. I've got to worry about resource management. I've got to do risk analysis. All those things will have to be done. They are like part and parcel of any project. And Six Sigma being lodged in a project mode, it will have to be done that way. Then you identify the vital few X to measure, analyze, improve and control. That's going to be the mission of your Six Sigma project. Measurements in Six Sigma. Now, what kind of measurements do we want to make? We got to measure these CTQs. Any instrument you are using, and this it goes without saying, if your instrument is poor, if the gauge that you are using, if the gauge is poor, there's going to be the data that it produces is also going to be poor. So you may have a perfect identification for the CTQ, but if you're not able to measure, those CTQ quantitatively, correctly, accurately, repeatedly, reproducibly and stably, unless you're able to do those things, if your measurement system that takes the CTQ, makes a direct measurement and produces data, if this system that is in between, this is a measurement system, if this does a poor job, there is no hope at all that you'll be able to ultimately control the final process, because you'll be working with garbage. You'll be working with data that has a lot of measurement errors. So you've got to make sure you do this measurement system analysis. And one of the key things there is doing gauge R&R. This is something that you should be able to do. So what are the steps in this measurement system analysis? You got to select the CTQ. That's like something you should be able to do. Then you got to be able to do the MSA. MSA is measurement system analysis. You validate the measurement system. You make sure that it produces accurate data, it produces repeatable data, it produces reproducible data, and it produces stable data. Once you've done that, we got to also make sure that I establish the capability of this measurement system. It by itself should not introduce so many errors that parts per million, when you try to measure it, those figures are wrong. It should not be like that. So it's a very important step. In fact, before you go into your improvement step, before you start making measurements and so on, that you make sure that the measurement system that you're applying to produce data out of the system, out of the process, that measurement system is worthwhile looking at. Then of course comes the analysis process. Analyze the process. Understand why the defects happen. This is the place where we are trying to do root cause analysis. The CTQs are the Ys. The CTQs, Y is the proxy for CTU, the critical to quality characteristic. What we are really after is identify those X's, the critical X's that have an impact on Y. Those are the vital few X's. If we control them, if we locate them, and then if we control them to the correct value, my Y or my CTQ is going to be it's going to be in control, and I'm going to have fewer defects. That's something I should be able to do. How do I get there? Well, the first step is, of course, I've got to map the process. Mapping is essentially flowcharting the process. I flowchart the process. I start from the input side and I end up with the output side. That's something I should be able to do. I must map every step of it in going from X to Y. That's something that we should be able to do it. While I'm doing that, I've also got to keep an eye on non-value added steps. For example, we should probably ask, why am I doing this step in the full process? And am I doing it correctly? Is the training there? Is the tools there? Are the tools there? The different equipment that I need and test equipment and so on, are they all there for me to be able to do that? Are the tools there for me to be able to carry out those things? Now, this will be done once I've got the mapping done, and I'm going to give you an example. Here's an example. The same Nissan problem. We took a look at the process And what did the process show us? The charting of the process showed that the first thing that was done in applying that logo on the back of the car, the logo was not welded. The logo was not welded to the car. The logo was taken, it was cleaned up obviously, and also the surface of the car was cleaned up. Then a glue was applied, some curing time was given, a foam was applied and some glue was applied, and then this thing was pressed on the body of the car. And people who do it well, they of course would position it very correctly and they'd hold it for a few minutes. Then of course they would let it go. That's the glue has cured, and of course the logo should stay there. So the steps of the process would be: clean the surface of the car, apply the foam layer to the logo and glue, apply pressure on the logo to attach it to the car body, and of course hold the logo, hold pressure for 5 minutes and then release the car to the next process. These are basically from left to right. This was the mapping of the process. With this map in front of us, a brainstorming was done, and all the factors that could have led to poor mounting. See that red box there? It shows poor mounting as the effect. Various things that could have caused it, those are listed here. For example, foam thickness could have caused this. Adhesion area, the area over which you apply the glue, that could have also caused this. The glue used, that itself could have probably caused poor mounting. The primer applied, the primer that was applied on the surface of the car, that also is something that could have caused the logos falling off. The thickness of the logo and perhaps its weight also. The duration of pressure, did I hold it for 5 minutes or 2 minutes or 1 minute? Then of course the amount of pressure that I applied in making sure that the logo is held close to that, held tightly against the body of the car. That's also something that could be a factor that could be contributing to this. Now this was done, this was done at a speculative level. No one really knew what the correct answer was. For that, of course, we had to get to the next step, which would be to try to identify what are the working ranges for these different factors. Those are shown here. These are the working ranges. If you look closely, the adhesion area, this is like one of the factors we see there. Type of glue used, thickness of foam, thickness of logo, amount of pressure applied, pressure application time, primer applied. They are the working ranges. So I have some choice there. It's not that I can't really change the adhesion area. The working range turned out to be 15 square centimeters to 20 square centimeters. I had that variation there. Maybe we were at 15. I don't know that at this point. But obviously, when we take a look at the process, when whoever was doing this project, when he took a look at the process, he might have found out exactly where things were as they were today. But because this working range was available, was Nissan using the optimum combination of all these different factor settings? Were they actually doing that? How would you find that out? And this is where you bring in statistical methods. You need design of experiments. So if you now see the progress of the Six Sigma project, you would probably find that now what they are trying to do is they are trying to establish y equal to fx, this relationship. Why is the response, which in this case could be the gluing strength or the amount of force that is required to push off a logo off the back of the car. This could be y, that could be the response, and the x's are those different factors that I showed you, the different control factors. And to combine all of them and to look at the effect, we had to do this. This trial had to be done in the design of experiments framework, and that would lead to finding the vital few x's that would have the largest impact on y, which is the gluing strength. How was that done? First of all, of course, the factors were, people did brainstorming and they utilized the cause and effect diagram to be able to do that, and I showed you that. Then of course the Pareto chart was used to try to basically find the relative frequency of different problems. And then of course histograms, correlation plots and DOE, these would be used to try to establish the relationship. Now let me just go back to the picture here for a minute and show you what is going on. The first is the mapping. This takes you from left to right for the full process. Brainstorming was used to try to construct this fishbone diagram, and then their settings were established by looking at the process itself. So this was actually to try to understand, first of all, try to understand what the process was. And even before this, if you looked at the Pareto thing, people went back to the problem there, problem statement, and they looked at other problems that also could be custom complex. They found that many customers did not like this logo business falling off, the logo falling off the back of their car. In most other situations, with most of the other things, they were pretty happy, but they are not very happy with this. So if you did a product analysis, you'd find many complaints came from this issue, the issue of the logo falling off. And that's why this became one of those targets for the Six Sigma project. Okay, so we had the mapping done, and we also had the working ranges identified, and we also understood what is it that we'll have to do. We applied the different techniques that were to be used there, and of course we had to make sure that if we're going to be measuring some forces, we had some device, and they had some device that they applied on the side of the logo. This is a mounted logo that was already cured and declared to be ready. Some force had to be applied on it to take the logo off, and that force had to be measured by some device, some gauge there. Was the gauge measuring numbers correctly? That also had to be established by doing what we call MSA, measurement system analysis. And many times, of course, they might, if this was like a routine process, they might also work out the CPK, process capability. Now that CPK in this case turns out to be 1 in 50 getting rejected. That's a pretty high level of rejection. Now we slowly move toward data analysis. Basically what we'd like to be able to do is we'd like to be able to see some patterns in the data. And one way to do that is if you've got multiple variables, to try to take a look at some correlations and see with those correlations, can we at least speculate about some cause and effect type of thing. This is something that will be verified by DOE, but when I make the correlation plots, do I get a positive relationship, or do I see a falling relationship, a negative relationship? If such indications are there on the what we call correlation plots, it would give us a pretty decent idea that perhaps I've located 1 or 2 factors that might be causing that effect there. 1 or 2 x values, x1, x2, x3. Remember, I had those factors there. In fact, I can show you those factors again. Those factors were the ones that were here. So what I would do is, I would basically do a plot of x2 versus y, x1 versus y, x4 versus y, x3 versus y, and see which of these show a strong correlation. That would show some sort of a linkage, some sort of dependency between x2 and y, or x4 and y. Once these correlation was sufficiently strong, I could use those as candidates. In my DOE, in my design of experiments. I could combine these factors in a matrix-like structure, which I'm going to show you in a minute, to try to sort of see, can I uncover some sort of dependency between these x's and the y's. This is something that I would like to be able to do with my DOE. All right, so coming back again to the slides, I now have my DOE guided matrix. This is my experimental matrix. If you look at it a little closely, you'll be able to see the pluses and the minuses under each column. Now let me remind you what this matrix is. This matrix actually is a scheme by which I'll be conducting my prototype experiments. So I'll be mounting a few logos under this setting. A set at plus level, B set at plus level, C set at plus level, D set at plus level. Remember now, D set at minus level. Remember now, each of these factors, we just chose 4 of them for illustration. Remember now, each of these factors had a working range. And let's just go back and take a look at them. The working range for these factors there. Here are the working ranges. So there is a high level, I may call it plus, and there is a low level, I may call it minus. So for area, I have 15 at high, I may call it plus, and 20 as low. And then acrylic versus urethane, this is also like, this could be plus and this could be minus, and thickness could be plus here, thickness could be minus here, thin would be minus. And as far as the thickness of the logo is concerned, thick is plus, thin is minus, and so on. So I do that. Once I do that, it becomes very easy for me to show that on my matrix here. So the first matrix will be done like this. Factor A set at plus level, factor B set at plus level, factor C at plus level, factor D at minus level. I run this process. I run the process now, A set at plus level, B set at plus level, C set at plus level, decent at minus level, and I check out the resulting gluing strength, and this is actually the sum of two strengths. So you did sample 1, you did sample 2, you added up this thing. So there may be some slight variation there. So you added up to take care of the fluctuation there. And I did the same thing. This was my experiment number 1. I would similarly do experiment number 2, experiment number 3, and so on and so forth. When all these experiments are done, remember this side of the matrix is an orthogonal matrix. It's an orthogonal matrix. It's an orthogonal design scheme, experimental design scheme. That's what I've utilized to basically show you this matrix on this side. It has got 8 trials. It's got 4 factors that are being varied according to the settings here. And these are the resulting numbers. So the first experiment, which was done at plus, 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 minus, it gave us a gluing strength of 9.8 pounds, then 8.9 pounds, then 9.2 pounds, and so on and so forth. And this guy gave 12.3 pounds, then 13 pounds, 13.9 pounds, and 12.6 pounds. You might think this is the best setting. We don't know that yet, because it's possible there may be other effects and not just an additive effect that is causing this. So I'd like to be able to probe this a little bit more. So what was done was the factor effect calculations were done, and then we tried to identify the effect of each of these values there. Now notice here, addition area, which is the first one, plus was low area. It showed lower strength. It showed, in fact, lower force required to move off that logo off the back of the car. And when area was increased, it required a higher level of force to move it off the back of the car. So this is like what we would expect. Same thing was looked at with factor B, that was the type of glue. It did not seem to have much effect. C also did not seem to have much effect. D also did not seem to have much effect, but area certainly had a large effect. And let me show this to you graphically. Graphically, the picture would look like this. Yes, of course, when addition area is changed from this low value to high value, which is like plus to minus, if you go by the working ranges that I displayed earlier, you'd find that gluing strength goes up quite a bit. It goes up by almost 50% when you move it from low area to high area. That is like setting of addition area from plus to minus. What about glue type? It does not seem to have much effect. So you could use either glue. You could use either level of thickness, that also would not be a problem. Either level of logo thickness, that also would not be a problem. But of course, if you really wanted to optimize the process, use these settings for your commercial production. Minor setting, which is a higher area for higher area, a larger area for addition area, glue type minus, thickness type plus, thickness setting plus for the styrene foam, and thickness setting plus for the logo. And these would then be your optimum setting there. Minus, minus, plus, plus. That would be the one that would be your new setting for the process. And you should then feel comfortable to release these settings now to your plant. And you could probably tell them, please go ahead and change the original settings by which you're applying this logo to the back of the car. Move them down to these new settings there, and make sure they have some means by which they can control these factors and they can keep them there. Because every car, as the cars keep coming by, you may actually have some variations in these input variables, these process control variables. One has to make sure that the process control variables stay exactly where they are found to be optimal. So that's like something that one will have to do. This is something that cannot be ignored. It happens so many times that you've identified the optimum settings, but you don't have the proper process control devices to be able to keep those process control variables there. If they are not kept exactly where they should be, lo and behold, it may turn out that the process will fail. This is something that you do not want to happen. That's why it's very important, and DMACC makes sure that you have a control step. You end up DMACC. You end up with these things. You have defined, you have measured, you have analyzed, you have improved, and you have controlled. This control one is kind of critical, because even if you've done all the other things right, unless you keep control in place, your process is going to wander off to some suboptimal value. and you will not be getting the kind of ppm defects that you're shooting for. That's something we got to keep in mind. So this is very important for us to be able to do that. You got to monitor the output. So basically what you really should do at this point is you got to keep track of this output as it comes off. So occasionally what you should do is you should take a car on the side and you should try to take that sticker off, that logo off. You should try to do that. You should probably measure. You should probably get down to the level of doing destructive testing, which is like you really peel it off, peel the logo off and measure that the force that is required to take it off. This way you'd be assured that my process is running at the setting where I set my process control system. Unless this is done, of course, it's very possible that the process would have drifted and then you'd end up with defective products again. And defective cars, when they go out with logos that fall off, again, there'll be unhappy customers and they may not really recommend those cars to their friends. That's something you got to watch out against. Once this is stabilized, you can hand over the process to the process owner, that is the assembly line. You could do that. That's not going to be very difficult. What things could have been done differently? Suppose you were doing this as a top-notch company. You are really a Six Sigma company and you have these defect complaints coming to you. What would you do differently? Let's take a look at all kinds of things that you could do. The first thing you should try to do is you should try to identify the critical to quality characteristics using QFD. Remember QFD, quality function deployment. This is something that actually takes it would involve interaction with potential customers or perhaps real customers, and we're using what we really try to do is we really try to make sure that the team understands what is it that they are really after. What are the CTQs? Remember this diagram, house of quality. On the left hand side, on the left hand wall, I've got the CTQs, the critical to quality characteristics. These are the ones customers are going to be really requiring. They are the ones who are going to be wanting to see these. And therefore, what we have to do is, for example, in the dry cleaning case, we wanted to make sure that we understood what the customers wanted. There, they wanted the dresses to be completely clean. They wanted perfect press. They wanted to make sure there were no delays at the counter. They made sure that there were quick turnaround. They wanted to make sure service was friendly. And of course, they also gave us some priority. So even in the logo case or any automotive application, for example, you'd be doing the same thing. You'd be interacting with the customers. You'd be preparing a list like this. And you identify these CTQs, you try to make sure you have some measures on them also. Because you can only control those things that you can measure. If you cannot really measure certain things, it's just going to be a feeling, just going to be a qualitative feeling. And that will be just good, bad, maybe type of thing. And you can't really do much quality control using that. So see if you can convert, or at least you can get a proxy for the CTQs that's measurable on some sort of a scale. And the moment you bring in this issue of measurement, you've got to make sure your measurement system analysis is complete and the data that you produce is repeatable, reproducible, accurate, and of course stable. Those things have to be made sure. After you've identified the CTQs by this quality function deployment, this CFD house, you got to find solutions. You got to find out then how am I going to deliver that. So in fact, if you recall the house of quality for the dry cleaning shop, to deliver these things, we got to have the experts tell us we must do good training. We must have good dry cleaning solvents, clean dry cleaning solvents there. We must have properly functioning filters. We must also have no rust in the those lines that bring the fluid into the system. The press pads must be firm, and we also have to make sure that the overall quality of the equipment is good, and we can do many other things. So this is something that I would start with. If you in fact go back and say how would I have started this, I would have probably done as step number one, I would have identified the CTQs by doing QFD. That's something I would have done. So I would have gone through this step. The next thing I would have done is something called design for Six Sigma. I'm actually getting proactive now. I have a tentative design. I have a tentative design in place. What I'm really trying to do is I have to identify and address weaknesses of that design. This is where we have to actually ask the question, how would this fail? How could this design fail, for example? If I've got anything, I've got a simple product here, I've got a pen in my hand. In what different ways could this pen stop working? That is the question I have to ask, and I have to construct this engineering worksheet, and that is called the FMEA, Failure Mode and Effects Analysis Worksheet. So that worksheet will be called an FMEA worksheet. And what this one really does is, it looks at two things. How might a CTQ fail? CTQ. I have a CTQ that fails. How might this happen? To be able to do that, I answer some questions. First of all, I try to find out what is the impact of this failure. This is the first thing I try to identify. The second thing I try to identify is what is the likelihood, what is the probability of this failure. If there is some item that has high impact, it's also got high probability, that becomes something critical for me. I've got to do some analysis beyond just doing plain and simple FMEA for it. I've got to take steps now at the design step to try to make sure this gets cancelled, this impact reduces, and also the likelihood reduces. Unless I've done that, I'll not end up with a good design. My good design will come when I've crossed this and I've crossed this, I've got a good design. So doing FMEA will lead to a good design. That is something I should be able to do. So this is something I would have liked to do if I was doing this place. In fact, if that had been done, if those trials had been done, then these logos would not be falling off in the field. That is something that's very, very important. And this is what is called design for Six Sigma. You're really designing things in such a way that it will lead to a high level of customer satisfaction, it will lead to very few defects. This is something that requires a lot of effort, of course. It requires a lot of prototyping and so on and so forth. You might use DOE. If you use DOE, you'd be doing this very efficiently. This is something that's routinely done for all critical products. For example, engineering products. A lot of electronic products that we have around us. When they go through the design shop, the designers, before they really start fabricating prototypes and all, they'll have the schematic, or they'll probably have sometimes even a mathematical model, or perhaps they have assembled something there. They start asking the question, how might this design fail? And what will be the impact? Will it stop working? Will it lead to a critical defect, or a functional defect, or perhaps just a cosmetic defect? What sort of defect will it cause? That would give you an idea of the impact. Then you will also ask, when this product is used in the field, how likely is it to fail? So this is now the issue of not the impact, but the likelihood. The product of these two quantities, which is impact multiplied by the likelihood of failure, this is the quantity that is called RPN, risk priority number. RPN. And the higher the RPN, the more dangerous that design is. The more likely that design is going to be, the use of the design going to be dangerous. So what we have to do is, we must identify the various modes of failure and calculate their RPN. And whatever turns out to have a high RPN, whatever mode of failure turns out to have a high RPN, we got to take steps so that we can reduce its impact, and also we can reduce the likelihood of that failure there. If we do that, we'll end up with a good design. Unless we are able to do this, that design is not really satisfactory as of this stage. So this is something I should be able to do at the design stage itself. So I would have done this differently. I would have probably gone through this, and I would have probably located then that the logo might fall off because of improper sticking, or not enough area, or not the right kind of glue, or the logo being too heavy, or whatever it is. I would have probably discovered that if I had done FMEA. That's something that apparently was not done when this was done. The third thing is, I should have actually optimized the mounting process itself. There again, my old friend design of experiments, DOE comes along. There I have these different process factors that I can play with, and I can construct this matrix. And with the help of the matrix, I may be able to conduct certain special experiments that will lead to an optimum process. Because here, each of these process factors that are like made to work together, those factors would have been set at their optimum levels. This discovery, of course, would take place through DOE. And again, I'm perhaps trying to oversell you this idea of DOE, but there is no better method available today. not known to man. We do not really know. We cannot really do one factor time trials. Those are bound to fail because many times factor effects they interact. You can't really do a study of one factor here, another factor there, a third factor here, fourth factor there, and hope that when I put the whole thing together, it'll all work just fine. It just doesn't work that way. Many times there are interactions, very complex interactions in systems, particularly those that are complex systems that are around us. Further, we got to do this DOE. We got to be able to do this. So if we did process DOE for this process there, we'd end up optimizing the mounting process itself, and that would have led to perhaps a process that would be guided by the black belt people, and that would end up with the correct choice of the X's and their settings to give us the best Y that is possible. Then the last thing I would have also probably done before I let this go would be to focus on the control system and perhaps plot some SPC charts. And the SPC charts could be done two ways. These could be utilized two ways. You see a chart there in the background. There is the trace of the level of perhaps the gluing strength. These probably I measure. These probably I measure as I take off a few samples off that production line there, and I do this. This obviously does not have to be done on the full card. You could just take a surface, a sheet metal that has been polished like the back of the card, and you could take a logo, and you could probably mount them. You could probably push it through the process of mounting, as if you're really simulating the real process. While doing this, you're recreating the process that would take place on the production line. And here you can play with the different factors, and you can conduct these matrix experiment, and you can get the factor effects and so on. If you do that, you'd identify the correct settings. Say you've identified the correct setting for gluing strength, areas, and all those things. Those could change while the process is going on. So what you have to really do is, you got to keep an eye on them. First of all, the output. Gluing strength being the output, you could plot a control chart for Y, the gluing, the force with which you can take the glue off the plate, of the metal sheet that is there. So you got the metal sheet there, then you're applying this. I'll pretend that this is the logo. I'll pretend this is the logo. And I'll put it there, I'll try to push it off. And this, of course, I'm doing with some device where I can measure the force. Once I'm doing that, I'll be able to generate some data, and that data I can plot. You see the control chart there? You see the control chart hidden there? That is the kind of chart I would like to be running alongside production that is going on there. This has got your upper control limit, lower control limit, and so on. We reviewed this thing when we were doing our review of SPC. So this is like something that I could do at the output level. I could do the same thing at the input level also, because I've got these X2, X3, X4. These were the three variables that I wanted to control, and I had to keep them at their target value there. This is something that I could also do, and this is something that I actually could do quite easily by doing this. So this is also something that I should be able to do. It's like it goes without saying that with such good controls in place, I'd end up with nothing except good products. How is it that I'm going to be delivering good results out of Six Sigma projects? Let's take a look at some of these things, and we'll come back and revisit some of the things that we've done so far in today's two sessions. We want to make sure that Six Sigma projects that we do, they deliver maximum results. And the aim really is, because we are putting in some resources, we're putting in some investment of time and resources to conduct these improvement projects. We really should be able to do this very, very well. We should be measuring the right stuff. So we should start with the customer, and we get the CTQs from the customer. CTQs are those characteristics, those quality characteristics that are important for the customer. This is something that's very, very important. Then, of course, the Y. Y is a proxy for that CTQ. So in our case, the problem really was that the logos were falling off. This is what the customer was observing. The logo fell off. So in fact, the measure that we had was, we had so many logos that fell off. What is it that was the good proxy for this? It was the gluing strength. It was the force with which we could take the logo off the back of the card. That would be Y. How would Y be controlled? What would be the different influencing factors? You remember those factors that we had? on the fishbone diagram, those were the different factors that could be affecting y. I had to do DOE. One had to do DOE to be able to find what exactly is the link between the x's and the y's. And remember what we did. We ended up with plotting graphs like this. These were the graphs that we used, and these show us the relationship between y, which is growing strength, which is on the vertical axis, and x, this is like x2, this is x3, this is x4, this is x1, and so on and so forth. So these are my process control variables, and I see their impact. These plots I could not have made. I could not have made these plots if I had run my experiments willy-nilly. It's only because I ran these experiments in this matrix framework I was able to run my trials, and I was able to plot those graphs there. Once the data is presented like this, once the outcome of the result is presented like this, almost anyone can actually point at the superior settings, the best settings. So in fact, it's really worth your time to do DOE. If you do DOE, if you use this matrix framework, which is like this one, and of course, to be able to do that, the first thing you should be able to do is, you should be able to do the cause and effect diagram. So this is what you start with. You've got the mapping done, and that mapping will inspire you to construct this cause and effect diagram with the problem at the end here. Then some of these factors probably are causing this thing, so you'd like to conduct some experiments with them, so identify their working ranges. So you got some choices there. Now let me tell you what different types, how many different ways you could run this process. There are 7 factors here. 7 factors here. These 7 factors each can be set at 2 levels. So if you look at the total number of combinations by which I could combine the 2 settings for each factor, there being 7 of them, is actually 2 to the power 7. 2 to the power 7 is the number. These many different ways I could actually conduct this process. I could run this process. And those would be the combination of the different working ranges that I have there. But this is just way too many. There's no way I would be able to find money to conduct all these trials. And if somebody could say, well, run all those trials. If those are the possible trials, go ahead and run them. The problem is I'll never have resources for that kind of thing. In fact, if you proposed a 6 exam project to be using these number of trials, nobody is going to fund it for you. So what do we do there? We bring in the knowledge of statistics. We bring in the knowledge of the master black belt. And the master black belt says, well, you don't really have to run these many trials. Instead, what you could do is, you could do orthogonal arrays. You could run orthogonal array experiments. That would reduce these 2 to the power 7 trials to 8 trials only. And this is a remarkable saving. This is a remarkable saving. You're coming down from 2 to the power 7 to 8 trials by using this approach to do your DOE. This is the framework for conducting your DOE. And that's what we see when we look at the matrix here. This matrix here is an orthogonal array. And this is good enough for me to calculate my factor effects. And this is good enough for me to plot these effects there. So whatever I wanted to do, of course, I'm not really reaching the ultimate optimum. I'm not reaching there, because that would be one of those 2 to the power 7 combinations that are possible. I just don't have the resources for that. But just see what this simple method has done for me. It has cut down the number of trials from being 2 to the power 7 trials to 8 trials only. And I've been able to find pretty decent practical answer. That is something I've been able to do. This is very important. Something we got to remember. If you run into a situation when there are many factors involved, in a process, and it turns out that you'll have really a very large number of trials to be done. For example, in this case, 2 to the power 7 trials. Think of either consulting with a master black belt or use your own training, pull out a textbook on statistics and start paging through those pages on orthogonal array designs and so on and so forth. And most likely you will not have to use what we call the full factorial design. Use the Taguchi type of design or use the orthogonal array designs. those are going to cut down the number of trials that you need to run drastically. So here we cut it down from 2 to the power 7 possible different trials to 8 trials only, and we got a very decent practical answer. After the changes were made, cars were monitored, the output was monitored, and the dealers, they sampled randomly 500 different customers. Not one had a complaint after the new process was put in place. That's a remarkable improvement. That's a remarkable improvement. From 1 in 50 logos falling off, they got down to the level 0 in 500. And of course, this was a sample, so most likely the population of the new cars, they had probably much better performance in the field also. What were some of the things that we did? Let's just try to recall some of the key steps there. This is going to be, if you start with the motivation is going to be your cost of poor quality. And where would you find them? Just go back to what we call the iceberg. Go back to the iceberg. Some of the problems are pretty visible. Some of the problems are visible, and they are the visible parts. Those are going to be the scraps, the rework, the warranty. Here also it turns out that most of the time what we really observe is scrap is reported and rework is possibly reported in the workbooks, in the logbooks. And warranty is also sometimes reported. These are the only visible ones. Now, many companies may think that this is the only consequence of poor quality. But lo and behold, because you've got unreliable machines, you've got materials that are not of good quality, because you've got production stoppages and so on and so forth, because of that, you're really losing a lot of money. You're losing the productivity of the capital that you employed in the company. And that is going to be the body of this. Look at the body of the iceberg. I've got conversion inefficiencies there. I've got inadequate resource utilization. I've got excessive use of material because quality is poor. Cost of redesign and reinspection, that also is there because quality is poor. Cost of resolving customer problems, that's also is going to cost the company some money. Lost customers and goodwill loss, that also is going to be there, and high inventory. You may not believe this, but when I did my master's thesis in Canada, systems were pretty unreliable those days. And there were production units that were like set up one after the other and so on and so forth, as we saw the production stages. And one of the problems that I was asked to work out was to kind of estimate the amount of inventory that you require between two unreliable production systems, so that the stoppage of one would not affect the operation of the second one. In fact, this inventory that was to be there in between would act like a buffer between two unreliable systems. So one, when it was feeding the other one, this inventory could absorb some of the problems that might be occurring with the feeding one and also with the breakdown one. In fact, this buffer sizing really became my master's thesis problem. And what was the system that I was working with? Unreliable systems at both ends. So I had two units that were unreliable, and I was supposed to work out the size of the buffer today. Today, even if one conceives a problem like that, he will be thrown out of a college. Because today we are talking Six Sigma, we are talking about perfection. We are talking about the level of quality that is right up there with those that are best globally. That's what we have to get to. So again, to come back to the iceberg, when you have to justify a project, take a good look at your cost of quality and try to see what you can do to try to improve the cost of quality that is there. And can you walk through the DMACC phase? Can you actually do that? If you're able to do that, you're certainly on that winning path. I hope you had an understanding now and also illustration with that Nissan project that we looked at, where there were defects and there were problems and there were multiple factors that could be affecting it. But with the DOE, with the framework that was DMACC and DOE put in place for improvement, the improvement step was there, we were able to take very good care of it. And defect levels came down from being 1 complaint per 50 cars to none in the 500 that were sampled randomly. That's a pretty big improvement. And hopefully you'd get inspired by this to adopt the DMACC procedure. That's like one if you're a practitioner. And certainly whenever you're trying to do an improvement, use the DOE framework, use the design of experiments framework. And there too in particular, try to apply first the orthogonal array framework. That is something that's going to save you a lot of time and a lot of resource. We'll continue. Thank you very much.